Hi there. We're talking about reactions in KMT. Now KMT is a short form. Obviously we'll talk about that in a moment. But just to follow along the logic of where we've been. We know what reactions are, we know how to balance them, we know how to predict the products a little bit. What we're trying to do is figure out a little bit more about them in how they happen. What's actually going on when we mix things together and get a reaction. So the KMT stands for kinetic molecular theory, and there's a few things about it that are going to seem really familiar, and there's a few things about it that maybe we haven't really thought about before, or we used to know, but well, we'll get there. So number one is that all matter is made of particles. Hey, that sounds really familiar. Awesome. We know those particles are in constant random motion. Heard that before too. The amount of motion, so the distance that each particle can travel, is going to depend a little bit on the state. So let me show you some, let's say, diagrams of particles in different states. We've got solid, liquids, and gases. Now if you look at it, the distance between particles of solid and liquid and gas are all different, and that's going to limit or influence or restrict how far each particle can travel. So in other words, solids tend to just wiggle back and forth or vibrate, whereas gas molecules, you can see in this diagram here, they're actually traveling around through space a bit, and we know that to be the case. A final thing about the kinetic molecular theory that's going to be important for us is that temperature is a measurement that reflects the average speed. Now it doesn't mean that solids move slower, they just move less. So they're vibrating very fast, whereas gas particles, because they're able to move more, then they will move more, but they're also traveling faster. So if the question was asked how a reaction happens, well, I can draw a reaction, I could have predicted the products, I can balance that, it's already balanced. But for me to think of that in terms of particles, well, I've got two diatomics, so I would draw something like that. I would draw the products, something like that. But does that tell me or show me what's actually happening to the atoms? Maybe. If I drew it more of a loose diagram kind of thing, I could draw that. And does that tell me what's going on with the atoms and the particles when they react? Maybe. So let's see if we can sort it out. In order for that reaction to happen, I need to break bonds. So hydrogen, we're hydrogen molecules. I need to undo that. The iodine, we're iodine molecules. I have to undo that. And then I have to make new bonds between the hydrogen and the iodine. Now we're getting somewhere, because now the question has to be asked, how did the bonds break? How did the bonds form? Well, there's our first question. How did the bonds break? Well, don't forget that a bond is one atom attracting the electrons of another atom, and that atom attracting the electrons of the first atom, or to put it differently, a mutual attraction between nuclei and electrons. So the shared electrons means both atoms are holding on to those both electrons. Well, if I want to break that bond, I have to undo that attraction between nucleus and electrons. That means I'm going to have to overcome an attractive force. That will require energy. So energy has to go in to break a bond. But where does the energy come from? Well, if we think about something we already know, we know that these particles are in constant random motion. So as they're in constant random motion, they're bumping into each other. Now, anytime you've bumped into something or someone, you notice the impact. And if you collide with the wrong person, you'll get a reaction. If you collide with somebody who's normally pretty even-tempered, but you hit them really hard, you're going to get a reaction. Now, obviously, it's not quite the same, but in terms of thinking about particles colliding and generating reactions, we're actually onto something here. You also need to have the right orientation. That's going to be kind of important. It's maybe less important for people, although if you bump somebody on the shoulder, maybe they won't mind so much as if you run into their face. But again, going from people to molecules, it doesn't always work well. So let's take a second look at it. And we're going to go back to that diagram that we had earlier. Will this thing work? Well, if those two particles collide as they are right now, Probably not, because you'll notice that the orientation isn't right. But if I turn both of those molecules a little bit and now have them collide in the same way, well, now they're lined up so that I could get bonds breaking, new bonds forming, and everybody's getting along. With the top one, maybe one hydrogen and one iodine would work out, but what about the other two? What about the other hydrogen and the second iodine? What about them? Whereas in the second orientation, we could just have a quick transfer. We'll swap the bonds from side to side to up and down, or actually the other way around. Swap up and down bonds for side to side bonds, and off we go. Now we're going to look at it as a structural diagram, or more of a Lewis diagram, because I think that will help us out a bit. We have the collision, so those particles come together and they collide with each other. There's enough energy in that collision to rattle things, to even break things, like break bonds. But when they collide, at first, you're going to have these bonds that start to break and bonds that start to form. So there's this moment where there's partial bonds. Now, if there's enough energy in that collision to break the bond, then we keep going, and we make the final products. Bonds continue to break, new bonds continue to form until they're completely broken and completely formed. If there's not enough energy, then that's not going to happen. If there's not the right orientation, then it's not going to happen. And there's other things that happen to either make a reaction work better or not so much. So, energy is required to break a bond. One thing I didn't mention earlier, but when new bonds form, energy is going to be released. So we often notice that during reactions, we get an overall output of energy. So if you set something on fire, you can generally stand around there and feel the heat. That's energy coming out. That's a result of all these new bonds forming. You can also manipulate reactions. And again, you know this from doing different things. Maybe you're trying to build the fire up, so you blow on it. Maybe you do something else. But there's ways that we can make reactions go faster, or in some cases reactions go slower, and it all comes down to changing something about collisions or orientation of those collisions or energy of those collisions. That's going to be our focus as we kind of pick this up and move it forward in class. But again, we'll pick it up and we'll move it forward in class, and we'll talk to you then. See ya.